Hello, good afternoon. Okay, the topic for this session is DPDK logs optimization and their new logs APIs. So here is the agenda. There have two parts. The generic logs and the ARM-specific log implementations. In the first part, I will give an introduction about our practice of optimization, the DPDK logs, and which include the spin log and the RW log. And we are trying to solve the spin log's unfairness issue, which we are trying to introduce the ticket log into DPDK. And to solving the cache bouncing issue, we are trying to introduce MCSQ spin log into DPDK. So in the second part, we'll talk about the ARM-specific WFE, wait for event instruction-based log to saving the interconnector traffic and the power. So okay. As we know, out of order execution and the compiler reordering is the strategies employed by the most modern CPU and their compilers. So observe the ordering of memory access may be influenced by the hardware and the compiler. And the ARC64 architecture has a weaker hardware memory model, which means it allows you to the processor to reorder, repeat, and merge access of the memory. So so one CPU core can see values change in the shared memory in a different order than other core wrote length. So basically, this kind of memory reordering is transparent to the programs most of the time. But still, there are cases where the observed memory ordering needs to be formalized. For example, the multi-thread circumstance. That's why the memory fence have been introduced. The memory fence can help Gavin observe the memory ordering. But memory fence will degrade performance. And the weak memory model typically suffers the most, we think. However, a compiler has support a relaxed C11 software memory mode in the atomic built-ins. So that's the approach for us to optimize. So basically, they have two sets of C11 atomicus in GCC, the atomic built-ins and the sync built-ins. The legacy sync built-ins are considered a full memory barrier most of the time. So in DPDK, the generic spin logs using the sync built-in to implementation the spin logs. The left side is a code snapped from the RT spin log, and it's assembling code of the log procedure. As we can see that the highlight part is full barrier. The DMB ISH instruction is a full barrier, which splits memory access in program order into two groups. So group 1 and group 2 separate. So observer will observe group 1 memory access before group 2. So that's break the out of order execution of the processor. So for atomic built-ins, it's a kind of a memory model aware atomic operation, which allows you to specify less restrictive memory barrier. For example, you can change from memory barrier to one-way barrier. The graph shows two kinds of one-way barrier: load acquire and store release. For the load acquire, all the loads and the stores of the shareability domain, which after the load acquire, will observed after the load acquire of the share domain. But loads and the stores before the load acquire will maybe observed after the load acquire of the shell domain. So for store release. So all the stores and the release of the shareability domain before the store release, maybe not maybe okay, well observed before the store release, and all the loads and the stores after the store release, maybe they were observed before the store release of the share domain. That's how it works. There's two kinds of one-way barrier. You can combine them to achieve your goals of data protection. So according to that, we implementation the spin lock in DPDK. We change the generic DPDK spin locks by using the atomic built-in instead of the single built-in. So and change the full memory barrier to one-way barrier. So we also did some benchmarking for this on several ARM SoCs. So as you can see that SoC number 1 with 3 GHz and SoC number 2 with 2 GHz. Here, the two kind of SoCs. So the red one is for sync built-in. The red one is for single built-in version, and the yellow one is for atomic built-in. So as you can see that on SoC number 2, the atomic built-in can gain performance around 3 times. And if you compare with those set and those two set of bars, you can see that there with more core involved into the clock contention, the performance will degrade. Yeah, after apply those two patches, one is for spin lock test and one is for spin lock atomic one-way barrier. Then under using this command line, you can get this. You can also do this benchmarking with micro benchmarking test. Okay, for RW lock, we modify the lock implementation. Similarly, change the full memory barrier to one-way barrier, and got the micro benchmarking results like this. Oh, sorry, like this. So as you can see that on SoC number 2, they also get some performance again. Because ARM have different implementation on its silicon, so we cannot guarantee that one kind of optimization can use to each of the platform. So on the weaker memory barrier hardware, so we can see that using the relaxed C11 relaxed software memory barrier can get performance, will benefit the performance, right? So how about using it on a stronger hardware memory barrier? So we did some benchmarking on x86. So these two set bus. This one is for the default inline assembling spin lock, and this one is for the sync built-in, and this one is for the atomic built-in, which this one is one-way barrier. So compare with the results, we can make a conclusion that the relaxed memory ordering atomic will not degrade spin lock's performance on the stronger memory model hardware. So during our benchmarking, we found that spin lock is unfairness sometimes. So as you can see on the right side, with 12 cores involved in the lock contention in the spin lock auto test, the core 22 and core 25 only can obtain the lock one time during the test. So that will stop in the core. So that's unfairness. So as we know, each PE will maintain the lock in its private cache. So when PE release the lock, it will invalidate the other PE's private cache. So when the number of cores involved in the lock contention, it will cause the cache bouncing. And the PE who owns the local cache is more likely to get the lock again, starving other PEs. And this starvation causes unpredicted waiting time for other thread. If this thread is related to the data path, maybe they will cause throughput decline. So the cache bouncing issue is once the lock acquired and released, the PE will invalidate other PE's private cache. That's kind of cache bouncing. And in some circumstances, if the lock structure share the cache line with other shared memory, the shared data modification will also cause the lock's cache bouncing. Yeah. So to solving the unfairness and the unpredictability issue for the spin lock, we're trying to introduce the ticket lock into DPDK. So ticket lock consists of two tickets, the current ticket and the next ticket. Here's the definition of the ticket lock. So it handles each request by increasing the next ticket, and each release will increase the current ticket. So finally, whose current matches next ticket lock. So this mechanism guarantees the FIFO service of the lock. We have already upstream dispatch into the community. If you are interested in this lock, you can put your comments there. Ticket lock has solved the unfairness issue, but it will also cause cache bouncing because they share the same, they're using the same structure. So to solve this, we are trying to introduce MCS lock into DPDK. MCS lock is a simple spin lock with each CPU trying to acquire and lock spinning on its own variable. The right side is the definition of the MCS spin lock. So it maintains a list of requesting order of the CPUs. So this guarantees FIFO service of this lock. And since it spins on the core's own local variable only, so that will remove the cache bouncing. So here is the paper which introduced this lock. So you can check this reference to get more details. So here I'd like to give a simple introduction about the lock and unlock procedure. So they have here are some graphics demonstrate the procedure of the lock and unlock. So in A, here in A, it's an embedded lock. So in B, CPU1 are trying to acquire the lock. So it will do a compare and swap operation with CPU1's MCS spin lock with the main lock. Because it's empty here, so it acquired the lock. Now it's running, indicated by the R. And in C, graph C, more CPUs are trying to acquire the lock. So first, let's say that CPU 2 first and CPU 3 second. Then CPU 2 will do the MCS compare and swap with the main lock. But lock has acquired by the CPU 1. So it will repeat the previous operation. Compare and swap CPU 2 with CPU 1's MCS spin lock. Then link with in queue the list. So len is the CPU 3. So the main lock are point to the tail of this queue. So once the CPU 1 has done, okay, here CPU 2 and the CPU 3 are blocked. So indicated by B. So once the CPU 1 has done with the lock, it will change the flag of CPU 2, then it's running. Same situation happened to CPU 3. So if no other lock acquiring for this lock, it will return to the situation of A. So as you can see that the pointer in the main lock is the tail of the queue of waiting CPU. So the locks we are talking about is all we are all making the lock requesting call busy polling waiting. So the current pose implementation will not suspend the call, suspend the execution. So the ARM has kind of waiting for event instruction, which can change time loop into the suspended execution, and which means there has less stress to memory subsystem. So and also it can save in power. So the benchmarking result shows on some SOCs that here in SOC number 2 with 96 core involved in the benchmarking. So it got performance boost. This micro benchmarking is not a real case, it's not a real life case. So okay, sorry. Okay. So let me make a conclusion. Okay. Sorry, out of time. Sorry, I didn't notice the hardboard. So for this, so all those patches are upstream. Some of them are under internal review. So most of them are upstream. So this to make a short conclusion of this. So we are trying to optimize with more performance, scalable,